All right, so today we're doing Unit 4, Lesson 8, Creating and Interpreting Graphs. So we're going to be sketching a couple of graphs today, so if you don't have that paper, go ahead and get your math notebook out. Which one doesn't belong? All right, so each of these don't belong for one reason or another. A is the only one that has a constant temperature the entire time. It doesn't change as the time increases. B is the only graph that has a maximum. So it's increasing and then it reaches a certain point in temperature and decreases at the same rate that it was increasing. Graph C is the only one that has only one minimum. And so it's also the only graph that has a negative temperature. So it's decreasing at a rate, reaches a minimum, and then increases back up at the same rate that it decreased. It also is the only graph that has two x-intercepts. So it crosses, so it has two x-intercepts. The other graphs do not even cross the x-axis. And then graph D is the only graph that changes direction and temperature more than once, because it's increasing, reaches a point, and then starts to decrease. And then it reaches a certain point, increases again, reaches a certain point, and then it decreases again. So it's increasing, decreasing, increasing, decreasing, so it changes temperature 4 times. All right. So what I want you to do is look at these graphs. We are going to be comparing the movement of a flag as it's being raised up a pole. And so graph A shows you that the flag is starting at 0 seconds on the ground, and then it's increasing at a constant rate. So it's going up, it looks like it's 1 second or 1 meter or 1 foot, depending on what your scale is. And so it's important for you to be able to interpret the situation and know what your scale should be. So it wouldn't make sense for this to be inches or centimeters or anything like that, because we're talking about a flagpole and you know that they're tall. So feet might be better or appropriate, or meters might be also something that is appropriate. Graph B, you see it's at 3 meters. Let's say meters is our height. And then it stays that height the entire time. So this might represent that the flag is already at 3 meters and it doesn't move as the time increases. Go ahead and see what you think flag C might be doing. All right, flag C looks like it starts at the ground. The guy might be pulling it up and then he readjusts his hand. So the height of the flag doesn't change. It's constant right there for a second, and then he pulls it the rest of the way up until it reaches the top. What do you think about graph D? Well, graph D might be someone who is inexperienced. So the flag starts at the bottom. He pulls it up till it reaches 2 meters, and then the flag falls back down. And he pulls it back up again, and it falls back down. And he pulls it up again, and it falls back down. And it does that 5 times. Graph E, this might represent the flag. You can see that it's not on the ground anymore. It's about a half a meter up. And then he pulls it up, readjusts his hands for a split second, pulls it back up, readjusts his hands so it's constant, and continues that until it reaches its maximum height. Flag F, you can see it's starting at the ground, and then he pulls it up at a constant rate, reaches the top, and then it goes back down to 3 meters. So this might represent that the flag was being pulled up. Oh wait, it needs to be at half mast today, so the flag is pulled back to half mast. So looking at each of these graphs, are they functions? What does something have to pass in order to be a function if we're looking at a graph? Right? That something is called the vertical line test. So if you can draw a vertical line on any graph and it only crosses it 1 time, then it is a function. If it passes more than one, or if it touches your graph more than one time, it is not a function. So all of these graphs will pass the vertical line test. So that also tells us that each input has exactly one output. So for every second in time, there's only one specific height for that time. So looking at this graph, could this graph be a representation of the flag, and is this a function? So definitely not. This is a vertical line. It looks like a flagpole, but it is impossible for this line to pass the vertical line test because it is a vertical line. So it has infinite solutions with a vertical line because they're the same thing. So it is also impossible for a flag to be at 1, 2, 3, 4, 5, 6 meters all at the same second. So what I want you to do, you need your paper and you're going to draw an X, Y axis. So you have a plane here, you have X, you have Y, and your X axis needs to go from 0 to 22 seconds, and your Y axis needs to go from 0 to 30. Go ahead and do that. And I'm going to play this video for you. As you watch the video, you need to be looking for key points of information like the minimum, the maximum, where it is at different times, and if it's increasing or decreasing. And you're going to graph what is going on with the flag to tell a story. Okay, now I'm going to play the video at half speed. Make sure you pay attention to where it's stopping and going back up and how long those pauses are. And the time it reaches the top and comes back down. Okay, so on your graph, you should have seen a kind of brief pause before it started because time started, the flag was not being raised yet. It didn't start being raised until 2 seconds. Some information that you needed to know was that the flag was already at 10 feet when it started, and then it reached a maximum height of 30 feet. So you can see at 2 seconds, it was at 10 feet, and then he raised it up, took a break at a little after 5 seconds. When then he got to 8 seconds, he started raising it back up, paused for about a second, and then he raised it up to the maximum height, which is at 14 seconds. And so you can see that at 14 seconds, it was at its maximum, which was 30. And then it stayed there until about 18 seconds and started to go down pretty quickly. And then it stopped at 10 feet where it started at. At 2 seconds, it's at 10 feet. So what I want you to do is calculate the average rate of change between when it started moving at 2 seconds and when it reached its maximum height at 14 seconds. So you should have in your notes that the formula to find average rate of change would be F of B minus F of A divided by B minus A. And so you should label this point A and this point B. And so your X value is your A, your Y value is your F of A, and B and F of B. So you can just plug those in. So we have 30 minus 10 divided by 14 minus 2. So you get 20 over 12, which is 1.67. So that tells you that it's increasing at a rate of 1.67 feet per second. And so that's how fast we know that the flag was being raised up. So those key features that we were talking about earlier, where it started, the areas and intervals that it's pausing and staying the same height, and then when it reaches its maximum and starts to come back down, are important features of the graph that you need to be able to identify and kind of draw out for different situations. All right, so this next example we're going to talk about is just to compare different rates of change on a graph based on the situation. So here we have a backyard party to prepare for, and parents are using 2 identical hoses to fill a small pool that is 15 inches deep and a large pool that's 27 inches deep. The height of the water in each pool is a function of time since the water is turned on. So our starting point is when the water is turned on. And so we're going to look at 3 different descriptions of each of these. So this first situation, each hose is filling up one pool at a constant rate. When the small pool gets filled up, the water for that hose is shut off. The other hose keeps filling the larger pool until it's full. So you can see that it's filling up the smaller pool more quickly than the larger pool. So looking at the slope of these lines, you can tell that the slope of the small pool is steeper. So it's going to have a quicker average rate of change, or a greater average rate of change than the small or the large pool. Okay. The second situation, the hose fills up one pool at a constant rate. When the small pool is filled up all the way, both hoses are shut off. So you can see that the large pool isn't close to being filled up at all, but the small pool is still filling up more quickly and has a greater average rate of change. Okay. Situation 3, each hose fills up one pool at a constant rate. When the small pool is full, both hoses are used to fill the large pool until it's full. So you have the hose in the small pool, so that rate of change is going to be the same. But then the large pool, you can see at this point right here, when the hose from the small pool is added, this becomes much more steep. So it becomes a greater average rate of change. Okay. So we can tell by looking at the graphs and the steepness which one is going to have a greater average rate of change. And so if we were to connect this line, you can see that those average rates of change would be the exact same. All right, hopefully this helps. And on your practice problems, you will be identifying average rates of change based on a graph and finding them by hand and kind of describing some situations.